programming languages such as Java allow you and in fact require you to define your own structured data types, and then object-oriented programming languages like Java and such then allow you to define inheritance relationships between these structured data types. Now Prolog, everything is different the way that we have already learned, and Prolog, well, how do the data types work in a language that doesn't have any data types? Well, in a sense, Prolog deals with the one data type, a Prolog term, so an arbitrary deep expression consisting of some kind of a functor part and then some number of arguments given in parentheses. When these arguments themselves can be arbitrary Prolog terms, so terms can be arbitrarily large nested tree structures, and then whatever other data we want, we need to somehow encode into this kind of Prolog terms that are internally defined as tree structures. So now if we think of this kind of a classic introduction hello world example, so create the toy bank account concept and then implement the simple familiar operations of deposit and withdraw and get balance. So in Java, so we would be defining this as a class, and in the class there would be data fields like the balance and the owner, and then the operations on the bank account, withdraw, deposit, get balance, they would be implemented as public methods, and then some of these methods would be mutators, so applying like a withdraw or deposit to a bank account object would then modify the internal state of that bank account, that if the balance data field was initially 500 and then you withdraw 300 from the bank account, so then the same bank account object is still the same object that you had before, but its internal balance field becomes 200. So this is how we program in an imperative programming language when data is mutable. But what about Prolog? So how do we represent this kind of a structured data, especially then difficulty with these operations, like you cannot, well, if you withdraw, so then you still don't modify the original bank account, but it's like you're creating a new bank account that is otherwise the same, but with a different balance. And let's see with this Prolog example bank account how this works. So we just make an agreement that, so for example, so suppose I create an account, and let's make this name so that it's gonna be echoed. So we're gonna create an account, then this predicate, you have it to take whatever you would make the constructor arguments in the Java if you made a bank account class, and then the result of this operation, so we make that the last argument, like the convention that the result is the last argument. So now we make an agreement, you gotta pick some kind of a representation as a Prolog term, so that the bank account, so just for brevity here, is a Prolog term whose functor is the word, is the symbol ACC. So remember, you can make up symbols to your heart content, and then the expression contains the values of this, what would be the data fields in a Java class, so the balance and the owner. So the operation of creating an account from this constructor parameter Ilkka here, so for who's gonna be the owner. Notice there is no constructor parameter for the initial balance because it's a 0 by default. So this creates an account object for which we now refer with the name A1. So this first example showing our encoding for a bank account. And then for each method that we would write into the Java data type bank account, the operations on the data, so deposit, withdraw, and get balance. So we then have to define these operations as a Prolog predicates, and we write the rules for them. These rules effectively saying like here is, let's look at this a bit more complicated series of queries that we're gonna be making here. So we first create the account for me. So with that account is known as A1, and then this form of these predicates. So because Prolog it doesn't have mutable data. Well, there might be some language specific hook, but even if there were, so that's now against the spirit of this whole thing. So we're not gonna be relying on those. That you can see that all of these predicates that correspond to the methods of the bank account object in Java. The predicates connect an existing bank account expressed as a term, as we have now agreed that the symbol is ACK, and then the data is there in the arguments, and then the additional like a deposit 200, and then in all of these predicates we always make the last parameter to be the new bank account. So we don't modify the original because Java doesn't have Prolog doesn't have a mutable data. But wait, so saying that if you deposit 200 to the bank account A1 that we created in this previous query in this particular top level query. So then the result is a new bank account named A2. And then from A2, so if we try to deposit the negative amount, so then well, we're gonna make that it doesn't fail, but this A3 is gonna be the same as A2, so that these operations can continue. Alternatively, you could make a version where trying to deposit the negative amount would simply fail. And then the same principle for these other operations that what in Java would be a method withdraw. So we implement as a predicate. So the first parameter. So again, the order of the parameters. You can always choose whatever you want. You just have to be consistent with your choice once you do it. But here I just follow the convention that the first parameter is always the currently existing bank account, and then the additional parameters of the operation. So in the Java version, so the withdraw would be, so you have to provide also the owner, so that well, I guess we would be having in a real banking there would be a password and other security, but just to keep this simple. So withdrawing 100 produces a new account A4, and then from A4, so then if we try to withdraw with the wrong name, so then again define it that nothing happens, so the new bank account is exactly the same as the original. And then so we look at what is this resulting bank account A5, so what is its balance and what is its owner. So let's query this and see what happens. So the end result of this operation is that the bank account A5 then its balance is 100 after these operations, and its owner is still Ilkka, as it probably should be. So looking at this, let's read through these rules that we given to these operations. So the create account, so just takes the arguments, and here so we don't do any kind of argument value checking. That of course could be them additional body to the rule, but then the result of this creating is just is a Prolog term, so starting with the functor ACK, and then packing the data of the bank account object into the arguments of this term. So if your data type, when you expressed it as a Java class, if it happened to have 5 data fields, so then your these corresponding Prolog terms, so after the functor ACK or whatever your functor name is, then would have 5 arguments representing that particular object. And then, so the rule for the deposit, so you can only deposit to something that is a bank account. So this is now good using the Prolog and its Prolog's compilers optimization and matching capabilities, so that this deposit is possible only if the first argument of the query so is something that is a bank account or unifies with. It could in a query, of course, it could be an unbound variable also. And then the additional argument for deposit operation, so the amount how much we are depositing produces a new bank account term that has the same owner. So if these structures get pretty complicated, like for example, if we have a binary search tree as this kind of a data type, and then we implement similarly the operations add, contains, remove, and such from the existing BST term produces a new BST term. So it seems kind of inefficient to create the entire new term, but because these terms they can freely share their subtrees, like for example, you notice that the resulting account, so it shares the owner with the original. So all these shared subtrees in these term operations, no matter which way your terms are branching. So then these shared subtrees are stored in the memory only once. So that's now the great advantage of immutability, that the immutable things can be freely shared by any number of simultaneous users. So of course we are using that ability here in Prolog to the maximum extent. So the condition for a deposit to happen, so amount has to be greater than 0, and if so, then cut so that we don't perform this other default kind of rule for a deposit, and then the condition just that the new balance so is the old balance plus amount. And now that we are using this is that evaluates the right hand side, so now both, so the balance has to be known and then the amount has to be known. So if we wanted to write this in a more reversible fashion using meta predicates to identify whether something is a variable or a bound term, and then these rules would become correspondingly that much more complex. But we're just doing a forward calculation like this imperative programming language. But even in this mechanism, so if you don't use if you use reversible operations in the body, so then these are still gonna be reversible. So you could do the calculation backwards, asking what would the original object the term would have been for an operation to produce a particular known result. And so the cut is at the line 5 is used to make sure that we don't execute this second rule for deposit. If we already seen enough, we commit to the fact that the deposit is successful. So if this cut doesn't get executed, so then this deposit notice again. So the first term, we always make sure that matching only terms of a particular type, that if somebody tries to deposit like to an animal or some other toy example, so then this deposit rule wouldn't be matching animals or whatever other toy domain we happen to have at hand. And so in the default rule, so often we see this don't care underscore, so no matter what the amount is, so then the result is just exactly the same as before. So now, why didn't we write this rule? Whoops. One more. So because these are exactly the same, couldn't we just say that the depositing, so anything to the account produces the same account, because we know that this rule gets executed only if the previous cut didn't happen. But now you could deposit like into a string or an animal, so we don't want that. So we write these rules so that they always require that the term that is participating in the operation is of a proper type. So then if we want to do like an inheritance, create like a savings account and checking account, so then the inheritance mechanism probably would get a lot more complex. But surely somebody's done that on Prolog also. Withdraw is with the exact same idea. So here the withdraw condition is that the owner so has to be the same as the owner of the bank account, the same parameter. So we just use the Prolog query term unification to enforce that both have to be equal. The owner again so doesn't change them. So the owner, it could be an arbitrary complicated term, and it just tags along in all these versions of the same thing. So these different versions, so let's make this visible for a moment. So take out all these underscores from the beginning. so that we can see how these resulting terms, these resulting data structures. So A1 is the account that we created, and then the result, well, A2 and A3 end up both being the exact same term, so not just equal term, but the actual exact same term. So every variable is a pointer in Prolog, so A2 and A3 pointers are pointing to the root of the same expression tree, and the same thing for A4 and A5. And for example, A5, so the account that results after all these first operations, so A5 is a bank account where Ilkka has $100 in it. So then we can, the get balance and get owner, so these would now correspond to the accessor methods, the ones that don't change the object state when you call them in Java. So the idempotent operations that just extract the information, so the balance of something that is again an account, that if we try to get the balance of an animal or a string or a list or something else, so it doesn't even match this particular query. So the balance of account that has the balance, and then the owner doesn't matter again, so it is the balance, and the owner of a bank account whose balance is something that we don't care about and has some kind of owner is then that particular owner. So this now demonstrating how this imperative programming and the structured data is done in Prolog. You choose some kind of a tree-like representation for your objects, your structured data, and then you just write the state transition rule predicate saying that if this is the current state of the particular data object and you perform this operation, so then the result is a new data object that can share some of the parts with the original, but then we have all these versions. This now what is called the persistent data in data structures theory. Now in computer science, the word persistent has two meanings. First, persistent data, the most common use of this term, data that outlives the process that creates it. So normally when you know that when you run a program in any language, so the variables cease to exist when the process itself terminates, but the files and databases are persistent data that continues to live on even after the original process has long since terminated. But in algorithmics, the term persistent data structure that has a different meaning. So it's not persistent in the like a database or file sense, but it's persistent in the sense that no data ever ceases to exist as long as it's reachable from our code. So notice we have all these versions of the exact same, so all these versions of this bank account, they exist simultaneously, whereas in Java and imperative programming languages, even if the object-oriented bookkeeping discipline is on top of the imperative programming, that in those languages, so a past doesn't exist. So of all the data, only the current version exists. But in functional and logic programming languages, because they don't have the destructive assignment and all the data is immutable, so we have all these versions of the data existing, and then we could go back to the past and branch to a new direction. So we could, for example, ask that if we deposit to this original A2, let's deposit 1,000 more, and that then gives us a new one, A6. So now what is the balance of A6? So the new balance is in this particular branch is 1,200. So we have all these versions that are still reachable from our code existing at the same time, and we can go back to the old versions and use them to launch a new future timeline. So now we have like two branching futures where the ending balance is stable. So both exist at the same time, but then they produce the different ending balance.